Here's the screencast for 2.4, which is the zeros of polynomial functions. So a polynomial function of n degree can have at most n real zeros. So for example, if it was x to the 6th, then at most we could have 6 zeros. So they either can be rational or irrational. So what that means is maybe these 6 zeros are going to be rational. So maybe they're 3, -2, 1/2, 1.7, 5/20, which is like 1/4. Need one more, how about like 1/3, 1/3. So these are all rational, or they can be irrational. So I could have the zeros be square root 3, square root 5, square root 6, maybe plus or minus all of those. So that gives me 6 zeros. So the rational zeros, literally, if you remember what rational means, they can be written as a fraction. The decimals actually stop. Versus irrational, go on forever. Cool, so this is just showing how to factor, find the zeros, and then we find them. Okay, so the rational zero theorem provides a way to determine a list of all the possible rational zeros of a function, but I have to warn you, sometimes the list is really long. So the next question is, how do we actually do it? So let's say you're given a polynomial. So here's our nice little polynomial. And degree is greater than 1. So that means we don't have any to the 0 exponents, and we don't have any, like our largest degree isn't like x to the -1. So our degree is larger than 1. We have integer coefficients, and our a of 0, which is this constant, does not equal 1. Then every rational zero f has the form p over q. Okay, so what we're actually interested in is the first coefficient and the very last number, which is our constant. So we have this p over q. So notice that p and q have no other common factors other than plus or minus 1. Alright, so here's our p, here's our q. P is the integer factor of the constant term a0. That's my p. Q is the integer factor leading coefficient a of n, so that's my q. Of course, the corollary is just the opposite. If our leading coefficient is equal to 1, then any rational zeros of f are integer factors of the constant term a0. Okay, so it's a lot easier to understand when we actually just do a problem. So we're going to go ahead and we're going to do example 1. List all the possible rational zeros of each function, then determine which, if any, are possible zeros. Which of them are possible? Okay, so first let's find what our p and our q are. So I know that my p is going to be, so I know my p is the integer factor, the constant term a0. So this is my p. My q is my integer factor leading coefficient. So I don't have a number here, but secretly we know that the coefficient right here is 1, so that's my q. And then what we want to do is put p over q. We want to list every factor of p over every factor of q. Alright, so let's see, I need to list the factors of 4. So I need to list my factors of p, which is 4. So the factors are going to be plus or minus 1, plus or minus 2, plus or minus 4, because those are the only things that can multiply to 4 potentially. And then I'm going to list my factors of q, which remember is equal to, which is 1. So my factors of 1 are plus or minus 1. Yeah, that's it. Okay, so we need to list these out. So I'll have plus or minus 1, plus or minus 2, plus or minus 4, all over plus or minus 1. Wait, so all that is equal to is, I have plus or minus 1, because 1 divided by 1 is 1. 2 divided by 1 is just 2, so plus or minus 2, and plus or minus 4. So we can begin by testing 1 and -1. So that's what I'm going to do. So I'm going to begin testing 1 and. So in order to test this, I have to do synthetic division. So I bring my 1 over, since that's what I'm testing, is 1. Right, I'm saying if x equals 1 is a 0. If it's a 0, that means I'm not going to have a remainder. Alright, so I bring all the coefficients down from my function. So I have a 1, I have a -3, -2, and 4. -2 and 4. Bring the first coefficient down. There's 1. 1 times 1 is 1. Combine -3 plus 1 is going to be -2. Multiply 1 and -2 is -2. Combine, so I get -4. Multiply these together, get -4. Combine, I get 0. Okay, so wait, this actually works. So this x equals 1 is a factor, which means, I'm sorry, it's a 0, which means the factor would be x minus 1 equals 0. Okay, so I have x minus 1, let me write it over here. So I have x minus 1, and then the quotient, it's being multiplied by x squared minus 2x minus 4. Let's see, because I started with an x to the third, so that's how I have to, so I know I have to start with an x squared right here. Let's see, is there any other number that we can we factor this any further? I'll let you think about it. So is there any number that multiplies to a times c, which is 4, -4, and adds to my b, which is -2? So I could have maybe like a 1 and a 4 here, but even if I like have one of them be negative, that only goes to, 3. What if I have -4? Okay, that would multiply. Issue is this only adds to -3. If I have the 1 be negative, this only, then the whole thing would be +3. Okay, so that's not it. How about -2 and 2? Well, those add to 0. This is it. I can't factor in any further. I cannot go any further. This is it. So the only 0 is x equals 1. That's the only real 0. That's it. I cannot factor this any further. Alright, so go ahead, pause the video, try out b, and then I'll continue to do it. Cool. So I want to list out my factors of p, list out my factors of q, find the possible zeros, go through test 1, and then find all the real zeros. So that's a little hint. So try to list out the possible factors of p and q. So we'll start off by labeling, this is my q, this is my p, because the p, alphabet goes in order, right? N, let's see, O, P, Q, well, I guess that didn't work out. I was just going to say P's at the end here. Mind your P's and Q's, I don't know. There's not really a good way to remember this. It's just P is the one that's on the right side, it's the constant, and Q is your coefficient in front of your exponent. So I need to list out the factors of P and Q. So factors of Q are going to be ±1 and ±2. Factors of P, 15, well, I have ±1, ±3, ±5, ±15. Cool. So the possible zeros are going to be P divided by Q. So we can go ahead and list them out. So I have ±1, ±3, ±5, let's see, 15, because that's if I divide everything up here by 1. And then I also have ±1/2, ±3 seconds, ±5 seconds, and ±15/2, because that's when I take ±2 and divide everything up there by it. Okay, awesome. So we found all the possible zeros. So the next step is to actually find the real zeros. So I'm just going to pick one. I'll pick one that's in the middle. So I'm going to pick 5. Let's see if this is a real factor. Alright, so I'll put 5 here. So I'm going to be dividing by, seeing if x minus 5 is a factor. So in order to know what goes here, I set that equal to 0, solve for x. Alright, so I have 2 here, -5, -28, and 15. Oh my god, +15. Alright, bring down the first one, multiply, combine, multiply, combine, so add, multiply. Oh my god, this actually worked. Check it out. First try, here we go. So, I have x minus 5. I also have 2x squared plus 5x minus 3. Right? So I need to factor this one step further. Let's see, x minus 5, 2x, x, because those will multiply to 2x squared. The only numbers that multiply to negative 3 are positive 1 and negative 3. And so the only numbers that multiply to negative 3 are either positive 1, negative 3, or negative 1, positive 3. How we know what to put in there depends on the middle. We're trying to get to a positive 5, so that means that I have to have it be positive 3. I need the bigger number to be positive, so that way when I FOIL it out, I'll have a positive number here. So plus 3, minus 1. So how do I know which one, where to put it? Maybe I put the plus 3 over here. Put the minus 1 here. So if I FOIL this out, I'd get negative 2x plus 3x. Wait, this has to equal 5x, not x. Okay, let's try it again. Put the negative 1 over here, and the plus 3 here. Okay, let's try it again. So I have 6x minus x. Oh, it's equal to 5x. Cool, so those are my zeros. So that's how I know. Alright, so my zeros are x equals 5. I set x minus 5 equal to 0. I see x equals 5. Set 2x minus 1 equal to 0. I see x is equal to a half. And set x plus 3 equal to 0. I see x is equal to negative 3. So those are my 3 zeros. That's it. So one way to narrow down the search for real zeros is to use Descartes' rule of signs. This rule gives us information on the number of positive and negative real zeros of a polynomial. So as you can see, that can take a lot of work. So something a little easier is Descartes. Descartes. I don't really care what you want to call it. It's just, this is a little easier. So how this works is you have the positive number of zeros is equal to the number of variations in sign of f of x, or it's less than that number by some even number, aka, let's say the example was there's 5 variations in sign, so that can mean I have 5 real zeros, or 3, or 1. Because I'm just subtracting by an even number, aka 2 until I get to 1. The number of negative real zeros of f is the same as the number of variation of sign of f of negative x, or less that number by some even number, or less than that number by some even number. So let's say if I plug in negative x into x, and there's 3 sign changes, I either have 3 or 1 negative real zeros. Okay, so let's see what this actually means. So I have x to the 4th minus 3x third minus 5x squared plus 2x plus 7. So the number of positive real zeros is going to correspond to how many sign changes there are. Okay, so I have a positive, I'm going to a negative, so this is my first change of sign. And then I'm going to a negative, well that's not a change of sign. And then I'm going to a positive, okay, so here's my second change of sign, negative to positive, and then I have positive. So I only have 2 changes of sign. Okay, and remember the number of positive real zeros is equal to the variations in sign, or less that number by some even. Okay, so 2 minus an even number, well 2 minus 2 is 0. So there's either 2 or 0 positive zeros. So the negative zeros means I'm going to plug in negative x into f of x, and let's see what happens. So I'll plug it in every single place. Everywhere where you see an x, I'm plugging in negative x. And let's see what changes. So negative x to the 4th is still x to the 4th. Let's see, x to the negative 3rd. So negative 1 times negative 1 times negative 1. Okay, so I'm going to have a negative, but a negative times a negative, because this is equal to negative 3 times negative x times negative x times negative x. So all these negatives are going to cancel out, so I'll have plus 3x to the 3rd. at negative x squared, still x squared. So it's positive because the negative will cancel out here. Negative times negative is positive. And then I have minus 2x plus 7. Alright, so let's go through it. So many sign changes. So this goes from a positive, positive, negative, oh, sign change, negative, negative to positive, second sign change. So I either have two negative real zeros, or less this number by an even, aka minus 2, or I have 0. So we can summarize this by making a little chart. Here's positive, here's negative, and here's total. Alright. Alright, so if I have two positive real zeros, I could either have 2 or 0 negative zeros. So that would mean, let's see, imaginary, oops, I didn't need to put total, I meant to put imaginary. Because remember, this is x to the 4th, so I have a total of 4 possible zeros. So if I have 2 positive and 2 negative, that means I would have 0 imaginary. If I have 2 positive and 0 negative, I could have 2 imaginary. Or if I have, let's see, 0, 2, 0. Or if I have 0 positive and 2 imaginary, I could have, 0 positive, 2 negative, I could have 2 imaginary. Or if I have 0 positive and 0 negative, I could have 4 imaginary numbers. 4 imaginary zeros. Cool. They all add up to the total possible. That's how we know. Alright, so try B if you can. If not, I'm going to walk you through it. Alright, let's go through. Let's see how many sign changes we have. So we go from a negative to a positive, so there's 1. Then positive, positive to a negative, there's my second change. Then here's my third change. So either I have 3 or 1. Because I have 3 sign changes. Alright. Let's go through. Plugged in for negative x. So this is negative 11, x to the 4th, minus 20, x to the 3rd, plus 3, x squared. I already plugged in negative x for my x. That's x plus 18. Okay, let's see how many sign changes I have. Negative, negative, oh, negative to positive, positive, positive. Okay, I only have 1 sign change. Interesting. Okay. Remember, we want how many real zeros there are. So we could do the same exercise that we did before, where I have positive, negative, and imaginary zeros. So either I have 3 or 1, and 1, and 1, okay. Because every single time I'm only going to have one only for my negative. I only have 1 negative 0. So I have a total possible of 4 zeros, which means every row has to add up to 4, so 3 plus 1 is 4, so I could have 0 imaginary. Or 1 plus 1 is 2, so I could have 2 imaginary. Those are my 2 cases. So complex zeros, this is what I've been hinting at. So complex zeros, a fundamental theorem of calculus, a polynomial degree of function n, where n is greater than 0, has at least one real or imaginary number in the complex number system. Meaning, a polynomial function of degree n has exactly n zeros, including repeated, in the complex. So what this means is when I said 4 possible zeros up here, that would mean maybe none of them are going to be, imaginary, as in this first case, but I could have 3 positive zeros and 1 negative, or I could have 1 of each and 2 imaginary. So every single time they add up to the total of my exponent. This leads directly to a linear factorization theorem, which states a polynomial function of degree n has n linear factors. Alright, so linearization, factor theorem, blah blah blah. It's better to talk about examples. So the example is, if I have a degree 5 polynomial, I have 5 zeros. This means I'm going to have 5 factors. 2, 3, 4, 5. Yeah, so I have 5 factors. So if I have a polynomial of degree 5, meaning 5th power, I'll have 5 zeros, 5 factors. Some of them might be imaginary, but that's fine. So a function has complex zeros when its factored form has a quadratic factor which has no real solutions. This is called an irreducible quadratic factor. Alright, so let's consider k of x. Right, k of x is the product of linear and irreducible quadratic factors. So let's go step by step. So the first thing I want to do is see what are my possible zeros. So I'm going to use my p over q. Let's see, so I have here, here, my p is negative 24, my q is 1. So, I'm going to be dividing by plus or minus 1 every single time. So let's just write out the factors of negative 24. So I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. Cool. Right, and so we want to do synthetic division until we have 0 remainder. So that's the goal. So we wrote out our zeros. That's step 1. Write out the possible zeros, then do synthetic until the remainder is 0. So that way we can actually factor this. Because our whole goal is to write it as a product of linear and irreducible quadratic factors. So to the 5th power means we're going to have 5 factors at the end. Okay, so let's start with, let's see, which number should we start with? You can try it out and then we'll get going. So if we try to use 1, that's not going to be really reasonable at all. We could use, see if it's at 2. Alright, so we're going to test if we have a 0 at x equals 2. Therefore, I'm checking if x minus 2 is one of my factors. So I'll put 2 here. So we're just going to use synthetic. So let's see, coefficient of x if it's 1. Then I have 1, negative 13, negative 23, negative 14, negative 24. Okay, bring the first one down, multiply, combine and add, multiply, combine and add. Let's see, so negative 7, multiply, oh dear, combine and add, so negative 37, multiply this out. Did I mess up? No, this is fine. No, wait. I think I'm okay. Cool. Negative 37 times 2, negative 60, 74. This doesn't seem like the remainder is going to be 0, because it's just going to give me a negative, negative. Okay, so I see already this is not going to work. Because if I keep doing this, I'll just get a big negative number. So for instance, negative 88, multiply by 2, get negative 176. Okay, and then I'll get a remainder of negative 200. So clearly we have a remainder. That's not going to work. So I'm going to restart. Here we go. So I know that that's not one of my factors. So what if I check for negative 2? Literally, we just have to do synthetic until we have 0 remainder. That's our whole goal. Okay, so I'm going to check negative 2. Plug in. So, decided to do this live without actually practicing. That way you guys can see the process. You won't always know what to start with. Sometimes you'll have a good guess. Like 2, I don't know, 2's solid normally, but that one didn't work out. So let's try negative 2. Combine, multiply. I don't know if this will work out. Let's test. Okay, it's 22. Oh, looks like it's gonna be nice. Negative 12. Oh, check that out. That actually works. 0 remainder, that means it's a factor. Awesome. So, I know that I have negative 2. Let's see. Negative 2 is what I'm dividing by. That means the factor would be x plus 2 times, let's say I started with the 5th, so this will start with the 4th, x to the 4th minus x to the 3rd minus 11x to the second. Let's see, minus x minus 12. Cool, that's fine. Okay, cool. So now I found one of my factors. I mean, we could just keep going down the list. Let's try again. I'm going to try -3 this time, but this time I'm going to use these instead. I'm going to use these instead. Try -3. I don't know, I could have chose +3, but I feel like it'll be -3. If I get it wrong, we'll just try it again. Whew. Alright, so coefficients 1, -1, -11, -1, -12. Hey, check it out. It's nice. I just copied down those coefficients. So 1, multiply, combine, multiply, combine, multiply, combine, multiply. Okay, guess what? This one works. Solid. Alright, so that's another one of my factors. So far I have x plus 2, I have x plus 3, and then I'm going to have that was is fourth, this is third, x to the third minus 4x squared plus x, oops, minus 4x squared plus x minus 4. Okay, so let's see if we can divide this out again. Fun stuff, right? I'll pick -4 this time. Same factors. Sorry, what I mean is I'm now going to multiply, now I'm going to divide this by x plus 4. See if it works out. Actually, I'm going to do it by x minus 4. Oops. Bring down the first coefficient, multiply this out, 0, 1. Multiply this out. Okay. So, I see I have no remainder. This means that I have x plus 2 as a factor, x plus 3, and this guy, I set x equal to 4, and he defined it, this is like in root form, and he didn't have it in factor form, so I have x minus 4 equals 0, so x minus 4 goes there. And then what I have left over is x squared plus 1. Okay, so this is an irreducible quadratic factor. That's what I mean. We can't reduce it. If I solve it, right, x squared plus 1, you know, set that x squared equals -1, square root both sides, I see x is equal to plus or minus I. Okay, so those are like my 2 roots in 1, 2, 3, and then 4 and 5 root right there. Yeah, we're just supposed to leave it as an irreducible. We don't want to reduce it, so I'm going to leave it as this x squared plus 1. There you go. Irreducible. Quad factor. Okay, so here I go. That's it. Those are like all my factors because this one is a quadratic, so it has 2 zeros. So it's a total of 5. B says write k of x is a product of linear factors. Oh, this is literally what I just did. I have x squared plus 1 equals 0. So x squared equals -1. So x is equal to plus or minus I. Now what I'm going to do is a product of linear factors, aka get rid of the quadratic. So still have my x plus 2, I have my x plus 3, x minus 4, but then I bring in my x minus I and my x plus I. Cool. So those are my 1, 2, 3, 4, 5 factors. And then list the zeros of k. Okay, so -2, -3, 4, -I, positive I. That's it. I guess I should have wrote them in order, but whatever. That's it. Alright, so write a polynomial function of least degree with real coefficients in standard form that has -1, 2, and 2 minus I as zeros. Okay, so pause here, give it a try. A little note is complex numbers come in pairs, so you should also be including 2 plus I. So this is a 4th degree polynomial. So we have 4 zeros, so we're going to have something with the 4th power. So your first step is to write the zeros as linear factors. Alright, so I'm going to go ahead, I'm going to distribute the negative. Distribute the negative out here. So I have, just going to do this first. So I have x minus 2 minus I. I have x minus 2, this is plus I, and x minus 2 minus I. So what I want you to recall is, because this is not easy to solve, so recall x minus 3 and x plus 3. This goes to x squared minus 9. So this is going to go to x minus 2 squared minus I squared. Awesome. And then we can just FOIL this out. Let's see. X minus 2 squared. So it's x minus 2 times x minus 2. So I have x squared minus 4x plus 4 minus I squared. Well, literally, minus I squared is literally just plus 1. Because negative I, I'm sorry. Oops. Because I squared is equal to negative 1. And if you have negative of negative 1, it's equal to 1. That's why it's equal to plus 1 right here. Okay. So, there's that one. If I add it, I'll have x squared minus 4x plus 5. Well, let's go ahead. Let's combine these two. That way I can just do 2 trinomials multiplied by each other. So I have x squared plus x minus 2x minus 2. Okay, so combine, that's minus x minus 2. And then I want to combine these 2 trinomials. So the way we're going to do that is we're just going to distribute. Just take each term, multiply by a term of the other. So multiply x squared by every single one of these. Distribute out. So I have x to the 4th minus x to the 3rd plus 5 x to the 2nd. Okay, so I'm going to pause it here, try it out, and then I'll show you. Alright, so this is what I got. So I just took each term, tried to color code it so you can see when I was distributing it out. So let's combine like terms. So let's see, x to the 4th is my largest one, so I have x to the 4th. That's the only one I have, so I'll cross it out. Okay, negative 4x to the 3rd, minus x to the 3rd. Those are the only 2 terms I have for x to the 3rd. So I have minus 5x to the 3rd, so cross those out. Alright, my x to the 2nd's term, so 5x to the 2nd plus 4x to the 2nd, that's 9x to the 2nd, minus 2, so that's plus 7x to the 2nd. Just trying to go through and go exponent by exponent. Okay, now I'm getting closer. Negative 5x plus 8x is plus 3x, and then I just have minus 10 at the end. Awesome, so that's in standard form. Goes from highest exponent to lowest. So you can totally do this. Alright, finding zero is a polynomial when 1 is known. So we've already talked about this. It's possible to use synthetic substitution with complex numbers in the same ways as with real numbers. This method can be used to find zeros of polynomials if one of its zeros are known. So find all the complex zeros of x to the 4th minus 6x to the 3rd plus 35x squared minus 50x minus 58, given that 2 plus 5i is a zero of p. Right. Then write the linear factorization of p of x. Alright, not gonna lie, this one is a challenge, but it's the last one that we're going to do for 2.4, so super pumped about that. Alright, so I'm going to take 2 plus 5i, and I'm going to do something like division with it. Just take all the coefficients of this function, so that's 1, negative 6, 35, minus 50, and minus 58. So go through, multiply this by, bring it down, multiply, so I have 2 plus 5i. So add these together. I only can add the real components. So I have negative 6, so negative 4 plus 5i. So now is where it gets tricky because I'm going to be multiplying two complex numbers together. So I'll take 2 plus 5i multiplied by negative 4 plus 5i. So I'll show you the first one, but the rest I'll just like pause and so you don't watch me write everything. Alright, so I need to FOIL it out. So I have negative 8 plus 10i minus 20i plus 25i squared. So plus 25i squared is the same thing as saying negative 25. So negative 8 and negative 25 is negative 33, negative 10i. Cool. So that's what I'm going to bring up here. So I have negative 33 plus 10i. Combine at least the real stuff because it's the only things I can combine, like terms. So I have 2 plus 10i. Okay, so come over here and I'm going to take 2 plus 5i times 2 plus 10i. Quick note that I wrote it wrong. I put negative 10i here, but then I need to change it over here. My bad. Alright, so you get 54 minus 10i, 54 minus 10i. Combine the real components. So, positive 54 minus 50, so 4 minus 10i. So I'll take 2 plus 5i times this 4 minus 10i. Okay, so we get no remainder. Awesome. Now what I want to do is I need to synthetically divide it again, because remember this started with x to the fourth, and this is going to be like x to the third minus 4 plus 5i times x to the second, blah blah, x to the first, and then this is x to 0. Okay. So I know that 2 plus 5i was a 0, and since they come in pairs, all complex numbers come in pairs, I know that 2 minus 5i is going to be another 0. So I'm going to do 2 minus 5i, and then I'm going to use the same coefficients. So I'm going to use these. Use these coefficients. So I have 1 minus 4 plus 5i, 2 minus 10i, 4 minus 10i. Alright, bring down the first coefficient, multiply it out, so it's just going to be 2 minus 5i. Interesting. So that goes, combine like terms, so the i's go away, this goes to negative 2. Oh, this is much easier to multiply out. So negative 2 I'm just going to distribute to each term. So I have negative 4 plus 10i. Okay, so this gives me negative 2. Multiply out, so I get negative 4 plus 10i gives me 0. Awesome. So I get no remainder again, and I even get no imaginary. Beautiful. Okay, so since this was to the fourth, this one would have been x to the third, which means I have x to the second minus 2x minus 2. I need to use the quadratic formula to find the factors. So use quadratic formula. So I know what that is. So to find my factors, I'll have x plus 1 plus square root of 3. Then I have x plus 1 minus square root of 3. That's how I got them from the quadratic formula. And then, because our idea, we don't write the linear factorization. That's our whole goal. So, to prove where I got this from the quadratic formula, I'll just do it over here. So, try it out yourself, but then you can see my answer. So this is using quadratic form. So, let's see, I want to write it, the linear factorization. So I know my other two terms, besides these, because remember it was 1 plus or minus square root 3, so this is, since those are my roots, I have x plus the positive 1 plus root 3, and I have x plus the negative of 1 minus root 3, right, because it's, the root is 1 plus or minus root 3. Okay, so the other two factors for my linearization are going to be x plus 2 plus 5i, and then I have x minus 2 minus 5i. Cool. Let's see, that's the linear factorization, those four. There we go. And the last thing I want to do is I want to write out all my zeros. So my zeros are going to be 2 plus 5i, 2 minus 5i, and I have 1 plus or minus root 3. Those are my zeros. And that's it. That's the end of 2.4.